Here's an example that's similar to the one we just looked at, but I've added a +1 around the self-application of f. So if we start evaluating this program in a rewriting view, that means we take this lambda, substitute it in for both of the f's, and now we have this lambda going in for f in the body here. That body includes a +1, so we'll keep a +1 on the outside, and then we have f applied to f. And if we take another evaluation step, that means we'll do it again. We'll take this lambda, substitute it in for these two f's, but we'll get another +1 on the outside, and we have to keep this other +1, of course. So we'll end up with two +1s. And if we keep taking steps here, the +1s will keep piling up. In fact, if we do this long enough, even if we just keep the current expression, then we'll eventually run out of paper to hold all the +1s. In other words, this is not a loop in the sense of the while loop. This is more like the recursive functionancy that eventually runs out of memory. Now, I've been talking about loops that either run out of memory or run forever, but there's a small step from that to reasoning about functions and how much space they use in terms of, say, do they use order n space in recursive calls, or do they use constant space? How can you know just by looking at a program whether it's going to have which of these two behaviors it's going to have? So I'll switch back over to Plait syntax, but here is an example of a function that runs forever. And the reason it runs forever is it's running forever because it calls itself every time. But it runs forever without running out of space because it calls itself in tail position. It's in tail position, tail meaning the very last thing we do in this function. That is, as soon as we get a value for this forever call, we have a result for the original forever call. And this is a syntactic property. It's because this forever call is the last thing inside the body of the forever, the last thing that we have to do. In contrast, here is a function that will run out of memory eventually. Right? It runs out of memory because the self call here is not the last thing in the function. When we eventually get a value back here, we will have to not that value. So conceptually, the knots all pile up. But another way to say it is the run out of memory is not in tail position, and so this is not what we would call a tail loop. The notion of tail position generalizes to other syntactic forms. Let's suppose we have a loop that has an if inside of it. Now, in this case, the self calls forever are not like the only thing in the body of forever. And this one even is not syntactically the last thing inside of the forever. But you know the way if works. If we'll get a value for the test expression, and then it'll evaluate only one of these expressions, and whatever we get as the result of this call, say, if we pick it, is the result of if, and therefore the result of forever. So in this case, both of the calls to forever are in tail position, because there's no work around them that needs to be done before we return from the enclosing call. Right? And to put it another way, in general, the two branches of an if are in tail position with respect to whatever the if is in tail position of. How about this case? Here I've got if again. The true and false are in tail positions, but that's less interesting since they're not calls. The self call here is in the test position. This is not in tail position because the test position of an if in general is not a tail call, not a tail position, because after we get a value from that, we pick one or the then or the else branch to evaluate. Right? So again, syntactically, the test position of if is not a tail position. Now this is all relevant to our lambda k interpreter, because if you look at the interpreter, then every time interp calls continue, the call to continue is in a tail position. That means that when interp calls continue, there's no more work to do to return whatever continue returns. Similarly, continue calls interp only in tail positions. That means when continue actually continues by interping, continue doesn't itself have any more work to do. So in neither case, interp or continue, are we building up the stack. There's one other recursive function, which is lookup, but if you look at lookup, you'll see that also lookup calls itself in tail position. So all of this means that the plait continuation, right, the do list at the plait level, which we don't have any control over directly how it's implemented, but we do have control over tail calls, and we've arranged that all of our interp and continues are in tail position, so the plait interpreter won't run out of memory. So if our curly program shouldn't run out of memory, everything will be fine. It won't run out of memory either.